So one of the very first reactions that we talked about in class was the precipitate reaction. Okay, and if you remember, the precipitate reaction was basically the formation of a solid. Now, when it comes to the formation of a solid, there's no change in the actual species of the reaction. For example, as we review, we've got something like iron 3 chloride that mixes with sodium hydroxide. Okay. When we predict the products there, we split it up. And, sorry, I have a stray mark there. And we find, just as a review, we find that we have iron 3 hydroxide, which is a solid, plus sodium chloride. And of course, this is unbalanced, but that's our idea of a precipitate reaction. And that's what the fact that there's a solid forming draws the reaction forward. There is another type of chemical reaction. It's actually probably what I would consider to be the broadest type is redox reactions or reduction-oxidation reactions. And once again, I'm just going to abbreviate. Wow, don't you just love my perfect handwriting when I'm on my iPad? That's a highlighter. Wrong button. Okay. So, these redox reactions, redox is short for reduction oxidation. Basically, a redox reaction is the reaction happens because there is a transfer of electrons. From one atom to the next. Okay, that's how those work. Well, it's not even from one atom, it's from one species to another. And we've actually looked at these before. For example, when we had something like sodium and it was turning into an ion, we actually saw something that looked like this. Okay, sodium plus an electron. Okay, in this case, the sodium atom, there we go, loses an electron. And this process is called oxidation. Okay. And the inverse is when something gains electrons. For example, we saw that fluorine would accept an electron to complete its octet and form the fluorine ion. So here we have fluorine gains an electron, which I wish I could spell. I don't know where I got that X from. But fluorine gains an electron, and that process is called reduction. Now, one way I remember that is oil rig. When you're trying to identify which process is oxidation and which is reduction. So, like I said, a way I understand that is something called oil rig. It's just a nice little acronym when you're having trouble remembering which process is which. And that stands for oxidation is loss of electrons. Oxidation is loss. And reduction is gain. And I'm going to run out of room. Okay. So when we look at an example reaction, let's say I have aluminum, the solid, and it's reacting with rust. Iron 3 oxide. What's going to happen here is this reaction is going to form iron and aluminum oxide. And this is why. So aluminum, and I'm not going to draw all the shells, but aluminum has 3 valence electrons in its outer shell. Okay? And it will give those electrons to the iron atom. Okay? When we look at this, we see iron is a +3. 3 plus. We're going to ignore the oxygen for now. Okay? So these electrons are going to be accepted by iron, and we get, what's happening here, and we get solid iron, which now has 3 valence electrons. We did not go over how to draw the Lewis structures for transition metals. I'm just doing this for convenience. And we get aluminum 3 plus. So what's really happened here is we have aluminum, and it's turning into an ion because it's losing 3 electrons. And those 3 electrons are gained by irons because we have an iron 3 plus. We add those 3 electrons, and we get iron solid. So this part of the reaction, since it's losing electrons, this is the oxidation part. Since this part of the reaction is gaining electrons, we call this the reduction part. Reduction. There we go. And one thing we have to remember about oxidation or redox reactions is they always occur in a pair. They always occur together. If the electrons are going somewhere, okay, they have to. They just have to go somewhere. You know what? I just realized I forgot to put a 3 plus here. There we go. So these electrons have to go somewhere. There are several ways we can see this, and several ways we can classify it. For example, when we see something like zinc reacting with hydrochloric acid, which I'm actually going to balance this equation. We see zinc reacting with hydrochloric acid, we get hydrogen gas and zinc chloride. Now this is aqueous, this occurs in water, but when we take a deeper look, we see that zinc, sorry I have a stray mark here and that bothers me. When we take a deeper look, we see that zinc is going from being a solid to being aqueous. And I know that it's 2 plus because it's bonded with 2 chlorines, and chlorine each has a -1 charge, and there are 2 of them. So zinc's charge, which we're going to call X plus X, has to be equal to that, or at least the absolute value of that. Now, another product of this reaction is, of course, the 2 electrons. And when we take a look at hydrogen up here, we take a look at it right here, and we divide it, what we see is I have a +1 and a -1. And I have this H+, which of course is aqueous, and that will turn into H2. I'm going to make that look like an H, just bear with me. And it's a gas. Now, since we have a gas, we know that this is a chemical reaction. Now, in order for this to happen, we have two H's. Sorry, I want to erase that. I decided I wanted to do something else here. Give me a second. We have two H atoms, each with a neutral charge. So that means I started with two H ions, and they're +1. So in this particular case, sorry, for some reason when I put my hand down, it keeps doing that. In this particular case, it took 2 electrons to get this part to happen. So when we look at this half of the reaction, what we see is zinc is losing electrons because it's a product, and that is the oxidation part of the reaction. Here we see the hydrogen ion gaining electrons, and that's the reduction part of the reaction. So that's what we've got here, is we do have a redox reaction because there's a transfer of electrons. And in fact, this is a special type of redox reaction. I'm going to rewrite it down here because I want to show you something. So zinc chloride reacts with blah, 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 blah. What we have here is that this zinc is actually, I don't want to do that. This zinc is switching places with this hydrogen. And we get our element, and we get an ion. This is called a single replacement reaction. In a single replacement reaction, oh goodness. In a single replacement reaction, in a single replacement reaction, an element becomes an ion. An element loses electrons to become an ion. And by the same token, an ion transfers electrons to become an element. In fact, I just realized I said something wrong here, and I'm going to hopefully fix it. It's not always that an element loses electrons, but it is always that an element transfers electrons. That's what I should have written. Transfers. Okay. And that's what we see here. Zinc has transferred electrons. Zinc has transferred those electrons to become an ion, and hydrogen has transferred electrons to become an element. Okay, that's just a gist of. That's just the gist of redox reactions. Combustion reactions are also considered redox, and we'll talk more about these later. But you'll have something like, and I'm not going to balance this, but you'll have something like C3H8 plus O2 will make, of course, all combustion reactions of hydrocarbons produce CO2 and H2O. Here we've got oxygen, and it's an element. And here, while not a formal ion, it does have a partial ion. It does form a partial ion state. We're just going to say charged. That's not an official term or a dictionary term. It's just what I like to call it before we get into redox numbers. So if you have any questions, make sure that you write those down. So, and always feel free to email me or anything of that nature. Okay. Next time we'll talk a little bit more about the other types of reactions.